numerical we do the numerical questions of chapter number 2. I solve the numerical questions from my personal book. Please do all the drill problems of the recommended book, and the recommended book is Engineering Electromagnetics by William H. Haight Jr. We follow the 5th edition of this book. So let us do the problems of chapter number 2. Example number 2.1. In example number 2.1, we have a charged particle of 1/9 microcoulomb, and this charged particle is located at the origin, that is at 0, 0, 0, and we have another charged particle of 100 millicoulomb which is located at 860, and these two charged particles are located in free space. Find F2 and F1. So let us calculate the force on Q2 due to the presence of Q1. The force on Q2 due to the presence of Q1 can be calculated with the help of this particular equation. Q1 Q2 into R2 minus R1 by 4 pi epsilon naught into the magnitude of R2 minus R1 raised to power 3. So you see R1 is the position vector of Q1. R1 is the position vector of Q1, and R1 will be equal to 0 AX. It will be equal to 0 AX plus 0 AY plus 0 AZ. This will be your R1. So R1 will be equal to 0 AX plus 0 AY plus 0 AZ. R2 is the position vector of Q2, and it will be equal to 8AX plus 6AY plus 0 AZ. This will be R2. So definitely R2 minus R1 will be equal to 8AX plus 6AY plus 0 AZ. As we are in the free space, so the constant of proportionality in the free space will be equal to 1 over 4 pi epsilon naught, which will be equal to 9 into 10 raised to power 9. So in free space, the value of this constant will be 9 into 10 raised to power 9. So let us consider the solution of example number 1 in accordance with this equation. So let us consider R2 minus R1. So R2 minus R1 will be equal to 8AX plus 6AY plus 0 AZ. We calculate the magnitude of this vector, and the magnitude of this vector turns out to be 10. And then we put the values on the right hand side of this equation. We put the values on the right hand side of this equation. So let us put the values on the right hand side of this equation. We have 9 into 10 raised to power 9, which is the value of the constant, that is 1 over 4 pi epsilon naught. Q1 is 1 over 9 into 10 raised to power minus 6. Q2 is 100 into 10 raised to power minus 3. R2 minus R1 is 8ax plus 6ay, and this is 10 raised to power 3, which gives you 1000. So we simplify the right hand side of this equation. If we simplify the right hand side of this equation, we obtain the force on the charge Q2 due to the presence of Q1, and this force is 0.8 ax plus 0.6 ay Newton. We know that the force F1, this is the force on Q1 due to the presence of Q2, and this force will be equal to minus F2, right? So F1 will be equal to minus F2. So definitely F1, which is equal to minus F2, will be equal to minus 0.8 ax minus 0.6 ay Newton. So this is example number 1. Let us do example number 2. In example number 2, we need to calculate the intensity, the electric field intensity in free space at this particular point. The point is in the rectangular coordinate system, which is 3, 0, 0. So we need to calculate the electric field intensity at the given point caused by Q1. You see Q1 is 9 nanocoulomb and Q1 is located at the origin. So the position vector of source number 1 will be 0 ax plus 0 ay plus 0 az. Then we need to find out the electric field intensity at the given point caused by Q2. The magnitude of this charge is 125 nanocoulomb, and this charge is located at 0, 0, 4. Right? And then finally we need to calculate the electric field intensity at the mentioned point due to Q1 and Q2 simultaneously. So let us do the first part of this particular example. Let us consider the equation for the electric field intensity. So the electric field intensity will be equal to Q1. Q1 is the magnitude of the charge of source number 1. R is the position vector of the point under observation. R1 is the position vector of the source, and 1 over 4 pi epsilon naught will be equal to 9 into 10 raised to power 9, and then we need to calculate the magnitude of this vector, and we need to calculate the cube of the magnitude of this vector. So let us consider R minus R1. You see R, which is the position vector of the point under observation, will be equal to 3ax. So R will be equal to 3ax, right? And you see R1 is the position vector of Q1, and Q1 is located at the origin. So definitely R1 will be equal to 0ax minus plus 0ay plus 0az. So R minus R1 will be equal to 3ax. So we calculate R minus R1, that is the distance vector extending from Q1 to the point under observation, and that is 3ax. The magnitude of this vector is 3ax. The magnitude of this vector turns out to be 3. And then we put the values in this particular equation. We put the values in this particular equation. 1 over 4 pi epsilon naught is 9 into 10 raised to power 9, and Q1 is 9 into 10 raised to power minus 9, and r minus r1 is 3ax, and then we have the magnitude of 3 in the denominator, which is 27. So the electric field intensity at the mentioned point due to source Q1 is 9 AX volt per meter. Okay. Now we consider the second source. The second source is 125 nanocoulomb. Here is the second source. The second source is 125 nanocoulomb, and this one is located at 004. So this point represent the position vector of the source. So the position vector of the source will be equal to 0 ax plus 0 ay plus 0, not 0, this is 4. So plus 4 az. This is the position vector of the source of part number 2, and definitely this position vector will be represented by r1 because this is the position vector of the source. And then we consider the point under observation, which is 300. So definitely the position vector of this point will be 3ax. So r minus r1 will be 3ax minus 4az. Anyhow, let us go to the solution of the second part. So for the second part, we consider this particular equation. We calculate the electric field intensity with the help of this particular equation. E2 will be equal to Q2. Q2 is the magnitude of the charge of the second source. R minus R2 is the vector which extends from the second source to the point under observation. 1/4 pi epsilon naught in this particular case will be equal to 9 into 10 raised to power 9. And R minus R2 will be the magnitude of the vector extending from the source to the point under observation. So as we have mentioned earlier, that R minus R2, which is the distance vector extending from the source to the point under observation, is 3ax minus 4az. We calculate the magnitude of this vector, and the magnitude of this vector turns out to be 5, and then we put the values in this particular equation. So we put the values in this particular equation. 1/4 pi epsilon naught is 9 into 10 raised to power 9. Q2 is 125 into 10 raised to power minus 9. The distance vector extending from the source to the point under observation is 3ax minus 4az, and we have got 125 in the denominator, which is 5 raised to power 3, which is basically the magnitude of the distance vector raised to power 3. So let us simplify this equation. So we simplify this equation. The electric field intensity at the mentioned point due to source number 2 comes out to be 27ax minus 36az volt per meter. Finally, we do the third part of this particular question. We calculate the total intensity at the mentioned point due to Q1 and Q2 simultaneously. So we take the vector sum of E1 and E2 and the vector sum of E1 and E2. The vector sum of E1 and E2 will be the total intensity at the mentioned point, and this total intensity will be caused by Q1 and Q2 simultaneously. So we add E1 and E2. The addition of E1 and E2 results in the total intensity. So the total intensity at the mentioned point is 36 AX minus 36 AZ volt per meter. So this was example number 2. Let us consider example number 3. In example number 3, we have a line charge which is extending from z is equal to minus 3 to z is equal to 3. So it means that the line is located on the z axis. The total length of the line is 6 meter. This line is extending from z is equal to minus 3 to z is equal to 3. The line charge density of the line source is known, which is 4 nanokilometer per meter. So this is rho L, the line charge density of the source. And then we need to find out, you see, the electric field intensity at this particular point. The electric field intensity at this particular point, the point is in the rectangular coordinate system. The x coordinate of the point is 0, the y coordinate of the point is 4, and the z coordinate of the point is 0 as well. So let us consider the figure for example number 3. This is the figure for example number 3. You see, we consider a line charge which is extending from z is equal to minus 3 to z is equal to 3 along z axis, and we consider the point on the y axis over here. So the point is 0, 4, 0. We consider a very small portion of the line which is represented by dl, and you see the position vector of the small portion of the line is r1, which is in the cylindrical coordinate system, which is equal to z, and the position vector of the point under observation is r, which is rho a rho. So definitely r minus r1 will be equal to rho a rho minus z a z, right? So this will be the distance vector extending from the small portion of the source to the point under observation. Anyhow, we calculate the electric field intensity at the point under observation due to the line charge with the help of equation number A. In equation number A, we need to know the line charge density of the source, the length of the small portion of the source, the vector extending from the small portion of the source to the point under observation, then the constant, which is 1 over 4 pi epsilon. We shall assume that the line is located in the free space, so 1 over 4 pi epsilon naught will be equal to 9 into 10 raised to power 9, and then the magnitude of the distance vector extending from the source to the point under observation. So let us go for r minus r1 on the next page. So you see r minus r1 will be equal to rho a rho minus z a z. The magnitude of this distance vector will be equal to under root rho square plus z square, as the source is located along z axis, so definitely dl will be equal to dz. So we put these values in the previous equation. We put, you see, these values in this particular equation. we put these values in this particular equation. So let us put the values in this particular equation. If we put the values in this particular equation, uh, you see we have row L, we replace dl by dz, and then we replace r minus r1 by rho a rho minus z a z, and this is the magnitude of the distance vector raised to power 3, which is rho square plus z square raised to power 3 by 2. So we assume that z by rho is tangent theta. Let us go back to this diagram. We consider this particular right angle triangle. We assume that z is the perpendicular of this triangle and rho is the base of this triangle. So if z is the perpendicular of this triangle and rho is the base of this triangle, then definitely z by rho will be equal to tangent theta. So we assume that z by rho is equal to tangent theta. So z will be equal to rho tangent theta, z will be equal to rho tangent theta, and dz will be equal to rho secant square theta d theta. So we need to find out the uh, the limits for theta now, because we have got d theta in this particular equation. It means that the new variable will be theta. So we shall calculate the angles with the help of this particular equation. Look at this particular equation. If we simplify this particular equation, theta will be equal to tangent inverse z by rho, right? So we will calculate, you see, the angle with the help of tangent inverse z by rho. You see, if you look at this particular diagram, if you look at this particular diagram, here is the point under observation, which is 0, 4, 0. So definitely rho is equal to 4. Rho in this particular diagram is equal to 4. So when z is minus 3, z is extending from minus 3 to z is equal to 3. So when z is minus 3, then we will have minus 3 tangent inverse minus 3 by 4, and this angle will be minus 36.8. and when z is plus 3, then we will have tangent inverse 3 by 4, and this angle will be 36.8. So you see, when z is minus 3, then theta is minus 36.8, and when z is plus 3, then theta is 36.8. So we put the value of z and dz in this particular equation. We put the value of z and dz in this particular equation. Okay, and the new variable will be theta, and you see the angle is changing from minus 36.8 to 36.8. Okay, so we put the values over here in this particular equation. So we have rho L, dz is rho secant square theta d theta, then we have rho arrow, and then we have z over here, so z is rho tangent theta, then we have 4 pi epsilon, and then we have rho square in the denominator, and then we have z square, and z square is rho square plus tangent square theta. We simplify this equation. Let us simplify this equation. If we simplify this equation, we get the electric field intensity. On the right hand side we have rho L, rho square secant square theta d theta, and then we have arrow minus tangent theta az, and we have 4 pi epsilon rho cube into 1 plus tangent square theta, and you know that 1 plus tangent square theta is basically equal to secant square theta, right? So we simplify this equation, so the electric field intensity will be equal to rho L divided by 4 pi epsilon rho. Then we have the integration, and you see the angle is changing from minus 36.8 to 36.8. We have secant square theta d theta, and then we have arrow over here, and then we have minus tangent theta az, and then we have secant square theta raised to power 3 by 2. Let us simplify this particular equation, okay? Let us simplify this particular equation. Okay, so if we simplify this particular equation, we obtain this particular equation. We have rho L divided by 4 pi epsilon rho. Then we have the integration from minus 36.8 to 36.8, and in the numerator we have tangent theta into arrow minus tangent theta, in the numerator we have d theta into arrow minus tangent theta az, and the denominator we have secant theta, and we know that 1 over secant theta is basically equal to cos theta. So 1 over secant theta is cos theta d theta, and then we have arrow minus tangent theta az. So we shall integrate cos theta, and then over here we have tangent theta cos theta, and if you simplify, you see this particular term. If you simplify this particular term, we have the integration of sine theta. So we have the integration of cos theta, and then we have the integration of sine theta. Okay, so we go ahead. We know that the integration of sine theta with these limits will be equal to 0, and the integration of cos theta is sine theta. We put the values in this particular equation. You see 1 over 4 pi epsilon naught is 9 into 10 raised to power 9. Rho L is 4 into 10 raised to power minus 9. We put the values in sine theta. So we put the values in the sine theta. We have 0.6 plus 0.6, and then rho is 4 over here. So if we simplify this particular equation, the electric field intensity comes out to be 10.8 arrow volt per meter. And you see arrow is along y-axis, so this is why arrow is AY. So this was example number 3. Let us do example number 4. In example number 4, we have got a surface charge which is located at x is equal to 0. So definitely this is an infinite sheet of charge which is located at x is equal to 0. If the surface charge density of the source is 17.75 into 10 raised to power minus 15 coulomb per square meter, find E8957 in free space. Okay, so we know that the electric field intensity at the point under observation due to an infinite sheet of charge is given by rho s divided by 2 epsilon into an, and we shall assume that this sheet of charge is located in free space. So if it is located in free space, then we shall consider epsilon naught. So let us put the values in this particular equation. Definitely an will be equal to ax, an will be equal to ax. So we have rho s, which is 17.7 into 10 raised to power minus 15, and then we have 2 into epsilon naught. So 2 into epsilon naught will be 17.7 into 10 raised to power minus 12. So definitely we will get 10 raised to power minus 3 AX millivolt, volt per meter, and we can write down this equation in this format as well. So please do all the drill problems of chapter number 2 from the recommended book.